everybody. Thank you for joining us today. Physical Sciences Grade 10 yet again. My name is Temba Ngube. I'm excited. Today we'll be looking at sound, which is a build-up to some of the concepts that we've discussed before, which is the transverse waves as well as longitudinal waves. Sound, I think, as you'd agree with me, is one of the most commonly observed phenomena in everyday, which is quite interesting in today's focus. So let's quickly have a look at what exactly we want to achieve by the end of today's lesson. Right, let's get right onto it. Okay. Right, as you can see on the slide there, sound is the broader concept. Now, we have already looked at speed of sound or speed of a wave in the previous sections. We have already looked at the speed, which has to do with how fast or the rate of change of distance in a given time. Okay, we're already familiar with the longitudinal waves in the sense that as far as longitudinal waves are concerned, of which sound is a typical example of that. Longitudinal waves, where we said the distance, the direction of movement as well as the disturbance are perpendicular to each other, which exactly what identifies a sound wave. We shall also look at the different properties of sound, which has got to do with pitch. Pitch is not entirely new, if I may also indicate. Pitch has a lot to do with the frequency, as you will establish right at the end of the lesson. Right, okay? Frequency there. And then also loudness, which is one of the very important aspects of sound, in the sense that when we talk about loudness, we're talking about volume, which is something that has to do whether the sound is softer or it is louder, lower volume or lesser volume, which is something that is very interesting as far as sound, because we tend to observe sound in almost every day of our lives, right? And then if you look at sound again, we shall look at reflection. Reflection has to do with a lot of the properties in terms of the echoes. We know the echo, you get into an empty room, then there's that, if you produce a sound wave, it bounces off obstacles or barriers, then you hear that repeated sound, which is what is very common. Hence I said, as far as sound is concerned, it has to do with a lot of everyday life situations that we are quite familiar with, which is what is quite interesting. Right, and then also we shall look at the applications. These two have a lot to do with the application of sound in nature, as well as in medical situations. Right, now let's, without waste of time, just to get us started, we shall briefly look at the key concepts which I've just introduced as far as the sound is concerned. You need to realize that as far as sound is concerned, some of the concepts we've done when we looked at longitudinal wave, and we want to very much at this point in time make it clear that as far as sound is concerned, it is a typical example of what we call a longitudinal wave. Remember, the wave is that series of disturbances that are propagated through a medium. So very key as far as sound is concerned. But let's quickly look at the brainstorming activity just to get us started. Right, now, sound investigation. I want us to think about this question: how can we hear, how can we be so sure sound is a wave? Okay, sound is a wave. We need to also, maybe that's one other area that you need to think of just to get us started. And then again, explain what happens when you clap your hands. This has to do with observations of what happens in everyday life. You go to church, we clap, somebody gets an accolade, we applaud, you know, we produce sound by so doing. So we want to put the science behind what happens every day and what we're going to discuss today in terms of the scientific concepts, right? And then the second one is the three sources of sound. Just list any three sources of sound, except, of course, for the clapping of hands. I'm going to give you exactly 2 minutes to look into that. Then we shall reflect in terms of the key concepts. Then take it from there. Let's get on to it, guys. All the best. Okay, guys, welcome back. Surely you have tried to figure out, because I want to think of this investigation in terms of trying to understand exactly how sound is propagated, and also verifying the fact that indeed sound is a wave, right? If we can briefly look at the first question in our icebreaker, how can we be so sure that sound is a wave? Remember, a wave is a series or a repetitive disturbances that are transmitted through a medium. Now, remember, when you clap your hands, what is actually happening? You are causing the air particles to be compressed. At the same time, the particles at some point they are further apart. So that repetitive movement of the hands causes the air particles. Let's think of the air as the medium, which is also very key, something that we've already looked at in the previous section. Right, now, sound is a wave in the sense that it consists of a series of disturbances, disturbances or pulses, okay? Disturbances or pulses, okay, that are propagated through space, right? And now, the space that we're talking about is a medium. Air is a typical example of the medium in which sound travels. Air acts as the what? As the medium. So now, you'd agree with me, as you clap your hands, you're compressing the air at the same, and then alternatingly, after that, you make the air particles in that medium to be kind of relaxed, which it takes us to what we've discussed in our previous section in terms of the compressions and the refractions, which are the key components of a wave. Then indeed, from that, with that kind of thinking, then we can say indeed sound is a typical wave. But what kind of a wave is that? Remember, the disturbances are back and forth as you clap your hands, back and forth, back and forth, back and forth. Right. Yet the movement is from the source, wherever the clapping of the hands take place, then it travels to whoever hears that clapping sound. So the medium becomes very important in terms of transmitting that disturbance in space. Right. And then a brief explanation as to what happens exactly. I think we've looked into that by saying that the air is compressed, so there'll be compressions, okay, which will alternate with refractions, not refractions. Let's remember that from our previous compressions and refractions. So this is a series, or it's repeated disturbances. We can think of these as disturbances that take place as you clap your hands, okay? Something which we commonly observe in our church, at school, wherever we go, right? That's why we say sound becomes a very integral part of our everyday life. So the science behind it is what is of interest to us today, right? So these disturbances are transmitted through a medium, right? The other three sources that we can maybe talk about, I know there could be a vast array of them that we could mention in terms of sources of sound. Remember, for sound to be propagated or to be produced by a source, there must be a vibration. That vibration must be repetitive, hence we refer to it as a series, right? So you can think of beating a drum, for example, as one typical example. A drum, okay, if you beat a drum, you produce a sound. Beat a drum, you produce a sound, okay, as well as if you blow a whistle, okay, let's say it's a sports day, as you remember now, it's the time for athletics. If you blow a whistle, you propagate sound. Now, what happens is the sound needs to be transmitted through a medium. Air, in this case, is one particular medium which is of interest to us in everyday life. So we know that for sound to travel from one point to another, there must be particles that transmit the vibration from the source, which does the vibration to whoever the listener or somebody who observes that sound. Then we know that yes, indeed, there is a source as well as the medium, and then there's a listener. So for sound to be produced, there must be vibration. That's the key idea, right? Okay, moving right along. Right, how does sound travel from a source? Right, we want to very much look at a simulation of some sort that will give us an idea exactly of what exactly happens. If you can check here, these are the particles. I think you could think of this as the air particles. I want you to pay careful attention to the red particles. The vibration is back and forth, back and forth, back and forth. And from our screen, the movement of the sound or the longitudinal wave is from our left to our right. Now, if you come to think of it, the disturbance and the direction of motion is in the same direction. Now, they are parallel to each other in a way. So this is indeed a typical example of how sound is propagated through space. Now, the source of vibration, if you can look, is the gray line, which continually moves back and forth, back and forth. Now, these particles, what they do, they transmit the vibration throughout the medium. So think of this medium as the air particles. Now, if you pay attention to the red, they move back and forth, back and forth, back and forth, yet the disturbance is transmitted from our left to our right. Come to think of it, this is indeed a longitudinal wave, which we have discussed in our previous section. Right, very interesting. There is a link there. You can check on that link to just to play around and make your own discoveries as far as how sound is propagated in space. Right, which is also a very important thing. Remember, sound is a longitudinal wave, as we have looked at in the previous concept when we started our session today. Right. Okay, wave properties of sound. Okay, what exactly do we observe with sound? Wave properties. This is primarily how sound behaves in space. Okay, let's take, for example, you walk into an empty room, right? What actually happens is when you shout, sound is propagated from your mouth as the source. You are the source of the sound wave. So these vibrations are transmitted through the air. Remember, in an empty room, there are no barriers. The sound wave will collide or will hit the walls and come back and get reflected. Then you hear that repetitive echo, which we call a reflection. We call that a reflection. So sound can be reflected, which is very key. Sound can be reflected. But if you get into a fully furnished room, what will happen is if you propagate a sound wave, some of the objects, the furniture will absorb those vibrations. At the end of the day, you don't get that reflection taking place. So barriers are what reflect the sound. So reflection, which we refer to as an echo in our everyday language, is one other property of sound, which is very, very, very important. Sound can be reflected. The other property of sound that we've also, maybe that we might want to think about, that we've also mentioned, is the one of superposition. Remember, sound is a wave. It means if pulses meet, either in phase or out of phase, you'd expect, according to the principle of superposition, that sound, those pulses, the algebraic sum causes a resultant disturbance, or the combined disturbance, which we used to explain the principle of superposition. So you can also think about superposition as a property of sound. Right, just for us to get a refresher, a break, give you a couple of minutes, then you refresh, drink water, and then you come back, and then we continue with our very interesting section and have a further focus on the properties of sound, which I find to be very interesting because they are quite relevant in our everyday life. Okay, let's take our short break, and then we join us on the rebound. Thank you. Welcome back, guys. A brief look again at the remainder of the properties of the wave. We've already looked at the reflection, which is quite common. The sound is propagated from a source. It is transmitted through a medium. It collides or it hits a barrier, and then it comes back. We hear the echo. Very interesting. So there is the science behind that. The medium which transmits the sound, and the sound hits a barrier, then that's reflection. That was our first property. Then our second property has to do with pitch. Right. When you talk about pitch, pitch has to do with the frequency. Remember, frequency has to do with the number of pulses, complete pulses or vibrations that are propagated in a given time, measured in hertz. Right. So if we talk of, let's say, for example, in music, say, for example, a soprano singer has a high pitch. Higher pitch has a lot to do with frequency. Let's have a look at that very quickly. Now, if you check as far as pitch is concerned, I'll model the longitudinal wave in the form of a transverse, like what we call, there's a machine that we call an oscilloscope. An oscilloscope, what it does, it records the sound in terms of amplitude versus time. We shall have a look at that. Now, I want you to have a look at this very quickly. Now, if you check, if this happens, say, in a second. Now, there are 2 complete vibrations per second. Maybe let's say these are our compressions, right? And then if that is our compressions, and then this is our refractions, okay? Right, refractions, right. Now, if, for argument's sake, this is a sound of a particular pitch. Now, and then if we're gonna have sound of a greater pitch, it will mean that, say, for example, we'll have 1, okay, 2, okay, 3, okay, 4, like that. So the one that is in pink in the other color has got a higher pitch, or because there are more pulses per second. Now, if you check the black one, the first one, there are only 2 per second. It means in this case, the first one, the black one, it will be 2 hertz, right? And then the second one, let's call that F1, for example, and then F2, let's say maybe because there are 4 complete cycles that were done in 1 second, right? Let's say the time is the same there, okay? If they were done at the same time, then this one is 4 hertz. Now, if we check, the first sound has got a lower pitch, the second one has a higher pitch. So you can think of maybe, let's say, the F2 as the soprano, or let's check maybe the second one is the soprano because higher pitch, and then bass. So there are fewer vibrations per second. Now, the other very interesting property of sound is loudness. You know, sometimes you observe a car collision, or let's say there's a lightning and thunder. You know, the loudness or the volume, the one that we adjust in your typical radio, the speaker is the output source. Now, if you talk of volume, we are referring to amplitude. We are referring to amplitude. Volume and loudness is to do with amplitude. Remember, amplitude exactly is the disturbance from rest position to the compression, or from rest position to the refraction. So the greater the amplitude, the higher the volume. So sometimes when we talk about amplitude and loudness, we would refer to it as volume. Very key. So the 3 very important properties of sound is an echo or reflection, okay, and the pitch, which has to do with the frequency. The higher the frequency, the higher the pitch, as well as the loudness, which has to do with amplitude. Greater amplitude, which means greater displacement from rest position to the compression, it means there's a louder sound or a greater volume. Right. Having said that, let's have a look at the key concept that has to do with these wave properties. Okay, let's model a sound. If you can look at this, these beads, they represent the air molecules. So the air molecules, in this case, they serve as our medium. Remember, the medium is the space which, the material which transmits the vibrations. So the speaker is the source, right, of the sound wave, because that's the one that vibrates continuously. So as the speaker vibrates, the particles near the speaker are compressed and refracted alternatingly in that order from the source to the listener. So as you hear the sound, you are the listener, or you observe the sound. All right, you are the listener or the observer of the sound. Okay, so what is very key is that you realize that these are the compression where the particles are high pressure or closer together. This is a compression, right? And then where particles are further apart is our refractions, right? Refractions, okay. So the density of this medium also will be very important. When we talk about density, I want to draw attention to density as a physical quantity. It's a very important one because it also affects how fast sound or a wave is propagated depending on the medium. So in a denser medium, you'd have particles much closer together. Let's say a solid being a typical example of a dense medium, which also transmits sound as a medium. And also you compare it to air particles, which are further apart. So the mass per unit volume in terms of density. Density, remember, it's mass over volume, mass per unit volume. So it has to do with how closely packed. The more closely packed the particles of a medium are, the higher the density of that medium. If they are not closely packed, say, for example, in a gas, it's a lower medium, which also affects the speed, something that we shall look at a later stage. Right. Okay. Now, seeing sound on an oscilloscope. We've briefly referred to an oscilloscope. Now, the vibrating speaker in this case is the source of our sound wave. Now, let's say this is the air particles. So what the oscilloscope has, it is a receiver or this is a microphone or whatsoever. What it does is it picks up the sound. So this period is the time, if you remember very well. And then what we have on the vertical axis is our amplitude. So the greater the displacement from rest position, the greater our amplitude. Right. So this is how sound is being produced from a source, and then the oscilloscope is just an output device which models it just like a transverse wave, but not exactly a transverse wave because this has a time component as well as the amplitude. Right. Okay. Moving right along, I want us to quickly have a look at the next slide. Right. The key concepts that have to do with the factors that affect the speed. Remember, speed is equals to V. Okay, the wave equation V is equals to F multiplied by lambda. Right. So this is the wave equation that we've discussed all along. We have also said that at times we can say V is equals to D, depending whether we're given the distance that is moved as well as the time taken to move that particular distance. So these are the two equations that we talk about as far as the speed is concerned. Right. So we've spoken about the density of medium. Now, a medium that has got a comparatively higher density, what it says to us is that the particles that transmit the vibration in that particular medium are actually closely packed. So the vibrations tend to travel faster in a denser medium compared to a less dense medium. Take, for example, in a solid, compared to a gas. Sound will travel much faster in a solid than in a gas. Right. So density of medium, the higher the density of medium, higher density corresponds to higher density corresponds to greater speed, right? Higher speed of sound wave. Okay, right. So the opposite is true. Now, the lower the density, the lesser or the lower the speed as well. Right. Now, the temperature of a medium at this stage, when we think about temperature in terms of coldness or hotness, but then remember very well in Gr10, we briefly looked at how matter behaves and the properties and models of matter when we said kinetic energy has to do with the temperatures. Now, at a high temperature, you'd understand the gas particles. Let's take air, for example, as a typical example of a medium. The gas particles will tend to move very fast at a higher temperature. Now, the higher the temperature, the faster the vibrations are transmitted from the source to the observer in the case of sound. So, at high temperature, you have got a greater speed because due to the vibrations that are being transmitted by the medium, right? So higher temperature will correspond to a high speed. At low temperature, on a cold day, sound will travel much slower. So high temperature, high speed, okay? So and on the other side, when you can say, okay, if the temperature is low, think of it on a cold day, sound will travel much slower, okay? Which is very interesting. Hence, I said in our introduction that sound as a concept, it has a lot to do with what we observe in our everyday life situations, which is very key. Now, come to think of it, coldness has to do with low temperature. Now, remember, if it's cold, particles tend to move slowly. You know, if it's cold, you move very slowly. You're not as energetic as on a warm day, maybe by comparison. So in terms of temperature, the higher the temperature, the faster the particles move or vibrate. So if there is a source of vibration, it simply means that these particles will be transmitted faster in terms of vibration by that particular medium, right? Which is very interesting. Right. Now, this is what is going to happen next. The other key concepts which we have to look at, relationship between sound. Now, we want to recognize at this stage that sound can be produced by a vast array of sources. We looked at the drum blowing the whistle, and the science behind that, which is what is common in all the cases where we can say, okay, this is indeed a source of sound. The source must vibrate and transmit vibration of the particles through the medium to the listener from the source. Right. If you think of it, we have then pure notes which are produced by musical instruments, if you can come to think of it, okay? Musical instruments, they produce pure notes. That's a violin there. You see, if you can check, this is a pattern, let's say, which can be produced by an oscilloscope. So these musical instruments, they particularly give us what we call instruments. They give us what we call pure notes. Then the piano, for example, is also, because it has different notes, I understand there were 6 of them or so, but now this is what happens when you propagate sound using a musical instrument. Now, when you talk of noise, we can think of the vuvuzela, which is a commonly used device or gadget in South African context. The vuvuzela does not produce a pure note, because if you check here, you look at that, the pattern which is produced by the oscilloscope, it's not as smooth as you'd compare it to the pure notes that are produced by musical instrument. So the vuvuzela will produce a noise. We love it, even though. Right. Then we have briefly spoke about the pitch. Pitch has to do with frequency, number of pulses that are propagated per second. Frequency, remember, is hertz, capital letter H, small letter Z there. So if you check here, the frequency of this one, it's just half, 1.5 or so oscillation or vibration. So this will be a deeper pitch. Think of it as maybe an output from somebody who sings bass in a choir, right? So the pitch is very lower there. But here we've got many complete oscillations in a given time. Provided these occurred at the same time, then we'd say, oh, this one is a higher frequency. This is higher frequency or higher pitch, okay? High pitch. So the word pitch and frequency can be used interchangeably to refer to one and the same thing. Very key, right? But now you would check also that the amplitude in these cases, in both cases, is the same. What we are mainly concerned about is the number of pulses per second, right? We have also briefly spoke about loudness. Loudness, music can either be soft or louder. Now, the key component of a longitudinal wave, which has a lot to do with loudness, is amplitude. Remember, amplitude is the distance or the disturbance from rest position to the compression, or from rest position to the refaction. Remember, we don't talk crest and trough, but we just model this as a form of a transverse wave, because it's the output. It makes it better for us to analyze, because it's a longitudinal wave. So we'll think of this loudness in terms of amplitude, right? So we shall always relate loudness to amplitude. And loudness can be alternatively referred to as volume, right? So the higher the volume, the greater the amplitude. The lower the volume, the lower the amplitude. So in essence, what we're saying, that distance versus that distance, the one which is louder is greater. Then we have got a higher volume in case, let's say this is case B and this is case A. So sometimes we'd refer to it as quieter or softer, right? Softer or quieter, okay? So softer, quieter goes with lower amplitude, lower volume. Louder goes with high amplitude, right? It goes with high amplitude, okay? It goes with high amplitude. Now, just for now, I think these are some of the very key concepts that we wanted to look into. We shall take a break for now, and then when we come back on the rebound, what we're going to do, we'll focus on the remainder of the concepts that maybe we need to understand as far as sound is concerned. Then we'll look at the problems that we have to attempt and then give feedback. Then let's take a short break, and then we'll join us shortly. Thank you. Hello and welcome back, guys. Hope you took your much-deserved break. Just previously, before we went for the break, we looked at the very key concepts. I think because we said sound is a phenomenon that just goes beyond the theory because it's so much every day, there's another component of it which is very key, which has to do with the application. Now, let's quickly look at how sound is, the science behind sound is applied both in the medical field as well as in nature, which is what is I really find interesting as far as sound is concerned. Right. Now, if you look at on this slide there, we have got ultrasound. Now, it will be very important for us to also mention the fact that as humans, what we hear is between 20 hertz and 20,000 hertz. Okay. What this simply means is that as humans, we can hear sounds of frequency which are in this range. So we shall refer to that as the human hearing range. That's the human hearing. So anything which has got a frequency which is greater than 20,000, take note there, 20,000, we shall refer to it as ultrasound, okay? That's the highest. Then the one that's below is infrasound. Infra, it means below the minimum. And then after ultra means beyond the maximum that we can hear. So now, because sound is based on the ultrasound, as one of the properties of sound, we spoke about reflection, right, which is a very important property of sound in terms of application. Now, when you talk about ultrasound, let's say, for example, this happens in the medical field, okay? It's in the medical field, in hospitals, your clinic, you name it, okay? Right, what exactly happens is that the ultrasound, when you go for a female goes to ultrasound, they'll be expecting maybe a child, you know, an unborn baby, which was so much excited about that, right? Now, what happens is the machine sends a very high frequency, which because it's ultra, is beyond 20,000. You can't hear that. It can penetrate through your tissue and it can get reflected back, and then an image of, in terms of how the young one, the unborn, is growing and developing. Just to keep track of that growth and development, they use ultrasound. So ultrasound is beyond 20,000 hertz. So you get to see the image there. It's based on reflection. Also, the baby there, which is a typical example of the application of sound, because we said sound is very common in everyday life. So this is in the medical field. How about the sauna? And one other misconception that maybe we need to clear, sauna has nothing to do with the ultrasound, the one that we spoke about. Sauna is to do with, as you can see, it stands for sound, navigation, and ranging. So this is what the bats used in nature. So this happens in what? In nature. This is how, remember, the bat can't see, but it has to hunt. Ever wondered how it finds its way or locates prey and be able to feed itself? It sends a very low frequency sound waves which get reflected from an object. Either the object will be moving or stationary, then it can locate it. Then by so doing, it can be in a position to catch its prey, which is very interesting, right? Now, so in nature, what these birds do, they send those low frequency, then when they can reflect, they can know the speed. Remember, speed is also to do with the medium in which the object, the vibrations or the longitudinal waves are being propagated. Or even the warships, they can also detect the position and the speed of submarines when they are in war. So they can also detect that. So this is a sonar, which has to do with the sound waves. Also, it's still based on the echoes. As you can see, the dotted lines represent the reflected longitudinal waves from the moving object back to the source, right? Which is very interesting, right? Then if you look at also the whale, this is how it locates the school of fish there. As you can see, it sends out waves which are get reflected. So this is one very important application. So in terms of applications, we spoke about nature, which has to do with the birds, as well as the fish in the ocean, the aquatic life. That's how they survive, right? And also we spoke about the medical applications. Very quickly, I would want us to focus on the questions, right, and check our understanding of our today's session. It will be very important also to pay careful attention to what exactly we take on, the three properties of sound, which is loudness, pitch, reflection, as well as their application. But as far as how fast a sound wave is transmitted through a medium, it will entirely depend on the density of the medium. The more dense the medium is, the faster the sound is propagated in that medium. Right, a brief focus on our questions. A car and the motorbike are involved in a head-on collision. So this is what happens in everyday life. Okay, let's look at the science behind that, which results in a huge noise. Remember noise, we've looked at the noise. Timber stands 60 meters from the collision. So this is the distance where he hears the sound crash. The sound wave travels. This is the speed at which sound travels in the air as the medium. So I just want you to quickly look at the two questions. I'll give you 2 minutes for that and briefly explain how sound is generated and propagated in order for timber to hear the sound. Calculate how long, okay? The emphasis on how long, remember, and then how sound is propagated in a medium. And then I will do that after the 2 minutes of your attempt. All the best, guys. So 2 minutes for that. Right, welcome back, guys. Hopefully you had a good, you took a shot at the two problems in the last 2 minutes that I gave to you. I just want us to quickly reflect on that and pay careful attention to the keywords in the question and also the concepts that we have discussed, which will help us in maybe responding to those problems appropriately. So, right. Now, if we can go to the next slide where we will do our feedback. Right. Okay. Just back a bit. Okay. Briefly explain how sound is generated in order for timber to hear the sound. Remember, in our discussion, we need a source of vibration. There must be a source of vibration. Source of vibration. In this case, when we talk about the source of vibration, is the actual collision that takes place when the two cars collide with each other. So once that happens, the air closer to the vibrations is compressed, and at some point it is also, the particles are further apart. So once we have that, we have got a series of vibrations that are transmitted through the air from the source where the collision takes place to timber. So air serves as the medium in which the sound is produced. So there's a series of vibrations or pulses. We can think of them as pulses. I think it would refer to one and the same thing, series of vibrations or pulses that are propagated as a result of the collision. The air is compressed, and the compressions and refractions are transmitted through the medium. That's how timbre actually gets to observe the sound. So timbre in this case is our listener of the sound. Now the air is the medium, and then the collision is the source of the vibration. So head-on collision, source of vibration, very key, okay? Source of vibration, okay? And then the air is the medium, now which transmits those compressions and refractions in that particular way. Now, how long? When we talk of how long, I think obviously time comes to mind. What exactly are we given? The 60 meters that is given to us in this case is the distance from the source of vibration to timbre, who actually observe the sounds. And then 340 meters is the speed. This is the speed. In this case, remember our speed is v, right? So what are we looking for here? We're looking for t, right? So we're given the speed and the distance. So as a result of that, we would say, we know that v is equals to distance divided by time, right? Then we do our substitution. Let's not make an attempt to manipulate the formula. Let's just substitute directly and then isolate what we're looking for. In this case, our speed is 340. Take care of the units. It's meters per second. It means our distance must be meters, and our time will also be in seconds because it's in meters per second. Then our distance in this case is 60 meters, then divided by time, right? So if we isolate the time, I think we multiply both sides by time, so we'll get delta t is equals to 60 divided by 340, right? So whatever we get here, we're going to equate it to seconds. It will be in seconds. That's our time. So we go to our calculator, right? 60 divided by 340 equals to, right? Okay, it's 0, comma, okay, let me adjust that, 0,176, 0,176 seconds. So this is our time. If I can clear that, okay, it's equals to 0,176 seconds. So that is the time that it takes timbre to observe that sound. Let's look at the further questions. Now it says timbre here is one of the people involved in the crash asking for help to be taken to, which is what was very sad, to hospital for a scan. Let's think about that. So scan, medical, okay? When she wants to make sure that the unborn baby is not hurt, on which principle or wave property is ultrasound based, okay? Principle or property, we have to mention one on which ultrasound is best. And then why is ultrasound safer, safety of ultrasound than X-rays, okay? Right, and then give one other medical use of ultrasound, okay, medical use of ultrasound. I'll give you a minute and a half to do that because these are direct recall kind of questions. There's no calculation whatsoever. So it's, okay, 2 minutes will work. It's based on basic recall. So it's either you remember this or you don't. So these are direct questions. I'll give you 2 minutes, so let's get on to it. Then when you complete that, we'll do our feedback together and wrap it up. Right. All the best, guys. Okay, guys, let's quickly look at the feedback on the three straightforward questions that I gave you to attempt. The first question had to do with the principle or wave property. Remember, ultrasound is based on reflection. Is based on reflection. But remember, ultrasound already is the sound which is greater than 20,000 hertz. Okay, so these are very high frequency waves. So if it is used, it is propagated from a source, it can be reflected back. So then we can check if the baby is heard or not from the reflection that we get. So think of it as an echo, right? And then the second question says, why is ultrasound safer for unborn babies than X-ray? So now in this case, we are comparing between ultrasound, sound wave, and X-ray. Remember, X-ray is somewhat dangerous because, as we shall establish in our following sessions, would realize that X-ray contains very high energy. So these ones, the ultrasound can penetrate and be reflected, but the high energy of X-rays becomes a bit dangerous for a baby, with the unborn baby, which is still developing at that stage. So ultrasound will be preferred instead of X-rays that we use to check for fractures in mature adults. And then the last question says, give one other medical use except ultrasound. We spoke about medical uses. We can also think about the flow meter, which checks if they are of the flow meter for the blood, if you can check whether there is a clot. Remember, if there is a blood clot, it means the arteries or the capillaries have got a small radius. Now, blood will be moving very fast, then it's high pressure. At times, also, low pressure can be a problem. So, you send the low frequency waves that are reflected back, then what the flow meter does, it picks up the speed of the flow of blood in a human being. So now that's one other very important medical application of sound that happens in everyday life, which is what is very key. Hopefully we had a very interesting session, but just to reflect on the key ideas that we looked on today, we briefly discussed on the wave properties, which is the pitch, which has to do with frequency, the reflection, the echo, the applications, all these are linked to what exactly happens in our everyday lives, which is very critical. I certainly hope you had a very interesting session today. Looking forward again to seeing you. For myself, Temba Nube, it's bye-bye for now. Join you later next time, same time. Thank you. Bye.